So now we have the solution to the telegrapher equations, the function with respect to position z for both the complex voltage and complex current along a transmission line. What do we do with these solutions? Of course, we can go through and pick any location on our transmission line, denoted by some index z, and insert that numeric value of z into those equations and determine the complex voltage and complex current at that point. Of course, the magnitude of the complex voltage and current tells us the magnitude of the voltage and current oscillation at that location. Likewise, if we determine the phase of those complex numbers, they will tell us the relative phase of the oscillations at that location. And so you can say, all right, it's a nice equation. I can punch the numbers in my calculator. It'll tell me physically what's going on. That's the usefulness that these equations provide to us. But if we look closer, there's more to it than simply using this equation as a guide to the order in which we should punch the buttons on our calculator. Math is the language of engineering and physics, and we need to learn to speak it. We need to look at the math and say, what is this telling us about the physical behavior of a transmission line? And if we do that, we find a lot of interesting things about what's happening on a transmission line, and we can use this insight to really go through and solve problems with transmission lines, to understand really what is going on and why, such that the answers we get make sense to us, and we can design circuits with those transmission lines that likewise make sense based on our behavior, our understanding rather, of the behavior of those transmission lines. So that's what we're going to try to do here. We're going to take our solutions and see if we can make sense of them, see if we can figure out what this math is telling us about transmission line theory. What we do here first is write the equations now in a little bit different form. And of course, our telegrapher solutions had two terms, sum of two different terms there for both voltage and current. And I'm going to go through and replace the math of each of those two terms with a more general form. So the first term I'm going to call V plus, and the second term I'm going to call V minus. Now, if you look down here, of course, V plus is that first term, V0 plus, this complex wave amplitude, this complex constant that we talked about. And then, of course, it's multiplied by essentially the first solution for the telegrapher equations, which is e to the minus j beta z. The second term, the V minus, now, likewise, is a mathematical variable name for the second term here, V0 minus times e to the plus j beta z, that being the second solution to our telegrapher equations. Likewise for current, I'm going to write it as the sum of two terms, and each term we can write in terms of the solution that we got for the telegrapher equations. Notice then that each of these two functions, or each of these four functions, I should say, are a function of position z, as well as the frequency of oscillation omega. And I leave those in right now. Eventually I'll leave off the omega, but right now I'm trying to emphasize that all the solutions that we have will change if we change the frequency of our excitation, the frequency of the source. So why do we go through and write the equations in this seemingly more abstract or complicated way? Well, it turns out that these functions, V plus and V minus and I plus and I minus, are very important physically. They're something that really tells us about what's occurring on the transmission line and about transmission line behavior. What we find is the functions V plus and V minus, as well as I plus and I minus, are a physical or mathematical description of a physical phenomenon that's occurring on the transmission line. What we find on our transmission line is that there are two electromagnetic waves propagating along that transmission line, one in the direction of increasing Z and one in the direction of decreasing Z. And those two waves, as they propagate along, each one individually will manifest itself as a voltage and current, and likewise the second wave will manifest itself as a voltage and current. And of course these manifestations will be lead to different values. They'll be different voltages and currents depending on the wave that occurs. Of course, the superposition of these two propagating waves gives us then the voltage and current of the telegrapher equations. So in the nomenclature that we'll use, V plus and V minus, V plus is the plus wave voltage. It is a voltage that is created by the plus moving electromagnetic wave, and by the plus wave we mean a wave that's propagating the direction of increasing z. The other wave is propagating the direction of decreasing z. We call this the minus wave, and it creates a current and voltage. The voltage that minus wave creates by itself is called the minus wave voltage, and of course we have the minus wave current. And so if we look on the preceding page where we sum these two terms together, the voltage for the solution for the telegrapher equations I sometimes refer to as the total voltage. It's the total voltage along the transmission line is a superposition, a summation of the plus wave voltage created by the plus going electromagnetic wave and the minus going voltage that created by the minus going electromagnetic wave. Now, this might make you nervous a little bit and think, gee, electromagnetic fields, why do we have this propagating electromagnetic wave, electric fields and magnetic fields? That's not something that we had to deal with in circuits before. But of course, they're always there. Anytime you have a voltage and current, you're going to have an electric field and a magnetic field, and vice versa. They'll couple together. You can't have currents and voltages without E fields and B fields, and vice versa. So it should be no surprise that if we have currents and voltages, we have electromagnetic fields. But in this case, along transmission line, we have propagating electromagnetic fields, one in either direction. So schematically, we can represent these plus wave voltage and current and minus wave voltage and current on our transmission line schematically. And I usually write them in some form, let's say that's shown here. The current that we have on our transmission line, again, is a superposition of the plus wave current and the minus wave current. But we're going to look at each of those two current components individually. And the circuit notation that we have for I plus, we write it as positive when going in the direction from left to right, the direction of increasing z. And of course, that's the same notation that we have for the total current when we sum the two together. And therefore, we use for the minus wave current, likewise, the same convention. The half cycle that it's moving in from left to right in the direction of increasing z, we call that half cycle a positive current, and the other half cycle then would be the negative. So again, we're not saying that the current, these two currents are moving from left to right. Of course, they're AC, sinusoidal. Half the time they're moving one direction, half the time the other. We're just saying, again, when it's moving from left to right, we call that half cycle the positive half cycle. The other one, therefore, is negative. When it comes to voltage plus and minus, we have kind of the same convention. We measure plus voltage from top conductor to bottom, likewise minus voltage from top conductor to bottom. Now I have these arrows that are here, and notice they're pointing in opposite direction. And the reason for that is these arrows indicate the direction of the propagating electromagnetic wave. This isn't the direction of the current or voltage. The current or voltage doesn't have a direction, but the wave propagation, the rate, the energy flow does. We'll find that the plus wave that propagates in the direction of increasing z, of course, then will carry electromagnetic energy from left to right. The minus wave propagating from right to left will carry electromagnetic energy in the opposite direction here. So this sometimes causes confusion with students, and I just want to clear this up, make sure you understand this. Even though I've written these things as two separate terms, together, summed together, of course, is the total current, and likewise the total voltage. It's not like the plus and minus wave current and voltage occupy the left side of the transmission line, and the minus wave current and voltage occupy the right side of the transmission line. Nothing could be further from the truth. The two electromagnetic waves, let's say the plus wave, propagates from one end of the transmission line all the way down to the other, and exists there at any given time all the way from one end to the other. It is a continuous electromagnetic wave that you can think of it as kind of a energy like a flow of water through a pipe here. It's not like a little burst that propagates through. It's a continuous flow. There's always electromagnetic wave at each and every location along this transmission line, regardless of the time. The same thing for the minus going wave. It's propagating along continuously from one side to the other. And these waves, again, they they don't have to miss each other. They don't have mass, so they will propagate through each other. They exist simultaneously in the same volume, the volume between the two conductors, generally speaking there. Sometimes students erroneously think the plus wave is somehow moving down the top wire and the minus wave is moving down the minus wire. And again, that's not true. A conductor, if it's a perfect conductor, cannot have any electric field, so there's no electromagnetic field in the conductor themselves. They propagate together through each other. There's no need to form two different lanes as if they were on an interstate highway, because again, neither of them have mass. So again, these are all together here. It's not like one's on the left side and the minus wave is on the right side. It's not like the plus wave is in the top conductor, the minus wave is in the bottom conductor. The current, plus current, for example, describes a function at every point along this transmission line from left to right. The minus wave voltage describes a complex function for every voltage along the transmission line, again, from right to left. So make sure that you understand. These terms that we separate out here, again, we've separated out to understand them physically. What is real in terms of what we can measure, of course, is not the plus wave voltage or the minus wave voltage. It's the sum of those two together. That is the solution to the telegrapher equations. That is what physically is occurring on the transmission line. That is what we can measure. The same thing for current. What we can measure is the sum of I plus and I minus. But we do have a mathematical description of each term, and we're going to look at that to understand what's happening on this transmission line. So each of the wave functions that we've just described, the plus wave voltage V plus and the minus wave voltage V minus, and likewise for plus wave current and minus wave current, if we look at each of those terms, we see that they have an exponential e to the either plus or minus j beta z, and each one has then a complex constant associated with it, one of our complex wave amplitudes, and there's unique wave amplitude for each of those four terms. So the plus wave voltage has a wave amplitude that we call V0 plus, the minus wave V0 minus, the plus wave current I0 plus, and the minus wave current I0 minus. And again, these are constants with respect to position z. They don't change with z. They do change with frequency. And again, I'll put that notation in there for a while before I drop that, to just emphasize that all this changes with source frequency. So again, we call these the complex amplitudes of each propagating wave, the complex wave amplitudes. And so make sure you understand that. That's what I'll refer to them as, the complex wave amplitudes. Now, do they have any physical meaning? Well, let's go through and look at our index for our transmission line and consider the index that we call z is equal to 0. Generally, that is the point at the very right end of the transmission line. We have z is equal to minus L here. We're increasing z, although z is negative, all the way up to z is equal to 0. That's the standard notation. We don't have to use that, but that's typically what is used. So for this standard notation, it would be this location right here. Let's see if we can determine then each of the wave functions at that particular point. We're going to insert z is equal to 0 into, for example, v plus, and see what we get. So we go ahead and we take our plus wave voltage. Again, this is the voltage that is created by the plus going electromagnetic wave. It's not the total voltage, it's just one component, one of those two terms. We evaluate at one specific index, z is equal to 0. And of course, this is going to convert a function of z into a specific complex number. So we have e to the minus j beta z. Now z is equal to 0. That's not z minus 0. That's z equal to 0 there. We evaluate that. Beta times 0, of course, is, or j beta 0, j beta times 0 is equal to 0. E to the 0 is equal to 1. And so we're left simply with our complex wave amplitude, V0 plus. And so we see mathematically that the value of this complex wave amplitude is simply the plus wave voltage, the voltage created by the plus wave, at the specific location of z is equal to 0. And that's where all the sort of subscripts and superscripts come into this complex wave amplitude. These are constants with z. We could have called them z1 and z2, or I'm sorry, c1 and c2 and c3 and c4 for constants there, but we chose to give them either a current or voltage definition, as well as these pluses and minuses and zeros. And so hopefully we can see now why. V0 plus is, in fact, the value of the plus wave voltage at z is equal to 0. The value of the plus wave voltage at z is equal to 0, V0 plus. All right, so when you see that number, right away you know exactly what the plus wave voltage is at whatever location on the transmission line is indicated by the index z is equal to 0. Now we could go through for the other three wave functions, v minus function of z and I plus is, function of z, and evaluate them at z is equal to 0, and we would get similar results. So v0 minus is simply the minus wave voltage when evaluated at z is equal to 0. Remember, the minus wave voltage is a function of position z normally, but we evaluate at one point, and then we get a number which happens to be equal to this wave amplitude v0 minus. Same thing for I0 plus, and the same thing for I0 minus. And so again, from the four complex wave amplitudes, we can determine the value of the voltage and current for each individual wave at one location only, and that value is z is equal to 0. So the four terms from our telegrapher equations, the V plus and V minus, I plus, I minus, they are complex functions of position, complex values. And so the question is, what does that mean physically? And so what we're going to do is look at the complex function, which is V plus, the complex function that describes the voltage that is created by the propagating wave in the direction of increasing z. And of course, we know that function to be equal to this. So what do we make of this physically? Well, like any complex function, we know that it represents or tells us about a sinusoidal oscillation. We have a linear system in a transmission line, and so if we excite it with a sinusoid, current or voltage of some frequency omega, then every measurement we make will likewise have the same sinusoidal frequency, be a sinusoid with the same frequency omega. And of course, that's true for total voltage and total current, but also for each component then of current and voltage, the plus and the minus. And so this describes then the magnitude and relative phase of the oscillation of the voltage created by the plus going wave at different locations z. To understand what this is telling us, we need to go through and do our uncompression algorithm. We need to go through and take our complex number and extract from it the values that we're really interested in with respect to our sinusoidal oscillation. The first thing we want to do, of course, is determine then the magnitude of that oscillation. The magnitude is a real value, a positive real value, non-negative real value, as a function of z. How big is the oscillation associated with the plus wave voltage? Moreover, how does that magnitude change as a function of position? We know as we move up and down the line, we'll get different values of magnitude. To determine what that is, we take the magnitude of this complex function. All right. So we get this, we can take the magnitude of that result, and the magnitude of the product of two complex values is the product of the magnitude of each. All right, make sure that you understand that. If I have the magnitude of a times b, where a and b are both complex numbers, then that's equal to the magnitude of a times the magnitude of b. All right. Now, remember, this doesn't work. This works for multiplication and division. It does not work for addition and subtraction. The magnitude of a plus b is not equal to the magnitude of a plus the magnitude of b. That's not the case for complex numbers, certainly, or any number, really. But in this case, we write this form. So we take this v plus, we separate it into two terms. We take the magnitude of each term and multiply them together to get the magnitude of the product. And of course, the magnitude of a complex exponential, remember, is always equal to 1. E to the minus j beta z changes as a function of z. It's a complex number whose phase changes with z, obviously, since it's e to the j beta, it changes with respect to this value b there. But the magnitude, when we take the magnitude of it, it's simply a value of 1. It does not change as a function of position. And so what we find here is that the magnitude of oscillation for a plus wave voltage is simply a constant with respect to position. If I go to one point of the transmission line, and if I were to measure simply the voltage that's created by the plus wave, and I measured its oscillation, it'd be a sinusoid. No surprise, it'd be a sinusoid. It'd have frequency omega. The question is, how big is the magnitude? All right, we can measure it at one spot. If we went to a different point on the transmission line and measured the same plus wave voltage, we find we get exactly the same magnitude. The magnitude is a constant with respect to position. Again, there's no value z that's in this result. There was a value z, but it was in the complex exponential, and the magnitude of that became 1. If we do the same thing for the other currents and voltages, and here I have a typo that says V plus, that actually should be V minus there for the minus wave voltage. We get the minus wave voltage as a function minus wave voltage as a function of position by taking the magnitude of the complex minus wave function, and that, again, because of the same arguments that we have here with the complex exponential magnitude equal to 1, it will simply be a constant. And again, the point here is you look at it, you see no index z. The magnitude of the oscillation of the minus wave voltage in this case is independent of z, meaning it is a constant with respect to z. The same thing for the plus wave current, and the same thing for the minus wave current. At every point we get an oscillation with frequency omega, a sinusoid, but we find that whatever that magnitude is at one point, it is at all other points if we're looking exclusively at V plus or V minus or I plus or I minus. All right, so what about the phase? And by saying what about the phase, I'm talking explicitly about the phase of the sinusoids for each of the 4 terms. I'm not talking about the phase with respect to the total voltage, the sum of the plus wave voltage and the minus wave voltage. We're just looking at the phase of the plus wave voltage by itself and looking at the relative phase of the minus wave voltage by itself, for example. So if we go through and look at the phase of the plus wave voltage, what we're looking for, again, is the phase of the complex function V plus. This is a function of position z again, simply the description of the voltage created by the plus going electromagnetic wave and the plus going electromagnetic wave only. If we go through and find that phase, what we find is a result that is given here. This phase term is the phase of the complex number of V0 plus. And actually, there's another typo there. That z should not be there. This should be a constant. V0 plus is a constant. So strike out the z there. And that complex number has both a magnitude and a phase. And so we separate this into the magnitude and the phase component there. And of course, we can group then this with the other complex exponential, and then from that directly extract the phase. So this is a value. This is simply the phase at z is equal to 0. It's just sort of a relative phase term. The important thing here is the second term. We see that the phase, the relative phase of oscillation for the plus wave voltage changes with respect to position. Remember magnitude, if we look at the plus wave voltage, if we know the magnitude at one point on the transmission line and we move over to another point on the transmission line, we would find we get exactly the same magnitude. It doesn't change at all. But for phase, it will change. If I look and I see an oscillation at one point on the transmission line, here, one point on the transmission line, and then I move over to another point, we find that the 2 points are not oscillating with the same magnitude, but they will not, generally speaking, be in phase. So what describes mathematically that change in relative phase? It's this function here, and the important thing, again, is the second term. What we find is the phase of the oscillation is directly proportional to the position z, the index z on the transmission line. The proportionality constant, of course, then, is a value which is minus beta. So we perform a similar operation on the minus wave voltage function, and again, this time trying to determine how its relative phase changes as a function of position as we move up and down the transmission line. We'll get a result that's very similar to what we had for the plus wave phase, but with one important difference. Again, the phase is proportional to the position z, index z. In this case, though, the proportionality constant is not minus beta, it's plus beta. And this is a very important difference. If we were to go through and plot the two phase functions, the relative phase as a function of position, with respect to index z along the transmission line from z is equal to minus L to z is equal to 0, what we find for the plus wave is we get essentially a linear function now with a slope that is negative rather, and for the minus wave we get a function that is again linear whose slope is negative. So the slope here is plus beta, the slope on the other term is minus beta. Now, what about these transitions that happen? This all of a sudden, this discontinuity in the phase. This is simply because we're plotting the phase over a 2 pi mapping from 0 all the way to 2 pi. Of course, we also could have mapped it from pi to minus pi. And of course, this comes from the Euler's equation. When we talk about a complex exponential there, it's in terms of cosine or sines. And so it is uniquely mapped only within the domain of 0 to 2 pi. And so with phase increases all the way up to 2 pi, instead of going beyond 2 pi, instead we zip back to 0. We're rotating around the unit circle, and we're going back to a angle of 0 once we get all the way around, all the way around 2 pi radians, for example. One last thing about beta, when we look at this, we do a dimensional analysis. Of course, the result beta z must be have units of radians, and of course z has units of distance, let's say meters, and so beta must have units of radians per meter, radians per unit length. And that's interesting with respect to comparing that to omega. Omega is radians per second, and so omega is what we call the radial frequency, a temporal frequency, a time frequency in radians per second. Beta I'll refer to as a spatial frequency. Its value has units of radians per meter. And we'll find that there is a close duality between omega and beta. So the electromagnetic wave propagating in the direction of increasing z creates a voltage and a current. We call the voltage the plus wave voltage and the current the plus wave current. Likewise, the minus wave electromagnetic wave is propagating in the direction of decreasing z, and it creates a minus wave voltage and a minus wave current. We've now gone through and looked and examined the mathematical expressions for each of those two manifestations individually, plus voltage and plus current, minus voltage and minus current. And what we found were that the mathematics were relatively simple. The magnitude, for example, of the plus wave voltage was a constant with respect to position. In other words, the magnitude of oscillation of the plus wave voltage is precisely the same at every location on the transmission line. The same is true likewise for the minus wave voltage. It too has a magnitude that is constant. It too has a magnitude which is the same on every place on the transmission line. Note, however, the plus wave voltage and the minus wave voltage are generally speaking far different from each other, but they're both constants. However, let's put the pieces back together. We say that the plus wave voltage and the minus wave voltage are just components of the total voltage. The voltage that we measure along the transmission line, we see mathematically consists of each two terms, and we've examined those terms and attributed each term to two different electromagnetic phenomena, one moving a propagating wave in one direction and one in the other. But this is what we measure, this total voltage here, the sum of these two complex voltages. And that's the key, that each of these representations is complex. Two complex numbers added together to form a third complex number. Now, here's the mistake that students often make. If I want to know the magnitude then of this total voltage, the magnitude that will measure along our transmission line, students oftentimes will say, well, gee, the magnitude of the total voltage is the total voltage just as a superposition of each of the two plus wave and minus wave voltages. The magnitude of the plus voltage and the magnitude of the minus voltage are both constants, so surely if I add the plus voltage and minus voltage together, the result will be a voltage whose magnitude is likewise constant with respect to position. And this is mathematically essentially what they're saying, that the magnitude of the total voltage is equal to the sum of the magnitude of each component, and therefore the result is a magnitude for the total voltage that is constant, just as the magnitude for each plus and minus wave voltage is constant. Now the question is that a correct analysis? Listen up. The answer to that question is no. It is not a correct analysis. Be very careful. I get this an awful lot. If we're adding two complex numbers together, the magnitude of the result is not simply the sum of the magnitude of each. Remember, that does work for multiplication. The magnitude of the product A and B is equal to the product of the magnitude of A and the product and the magnitude of B. But when we're adding two complex numbers, then the magnitude of the sum of two numbers is not the magnitude of the first plus the magnitude of the second. And so this expression here is completely incorrect. All right, this is not valid. This is sloppy mathematics. Oftentimes, students will write this down, I think, just thinking that, hoping that it's correct. Well, it's not correct. All right, so we cannot conclude that the magnitude of the total voltage along a transmission line is a constant, even though the magnitude of each individual component is. And the reason, again, is because the two components are complex. They have a magnitude and a relative phase. Maybe the two components will add such that the phases are the same that would increase the magnitude. At other places, we'll find the phases are going to be out of phase, and they'll add in a way that decreases the total magnitude. And we'll show this later, but what we'll see is that if we were to plot the magnitude now of that total voltage, the voltage we measure when we have two waves propagating in opposite directions, would look something like this. For the magnitude, we'd have peaks and we'd have nulls. For certain circumstances, we can find that the nulls are so small that they can even go to zero. We can have locations on the transmission line where the total voltage is equal to zero under certain conditions, and we'll talk about that later. So the magnitude of the total voltage is what? Well, the magnitude of the total voltage is simply the magnitude of the total voltage. You can't determine it from knowledge of simply the magnitude of the plus wave voltage and the minus wave voltage. It is a complex summation. And this kind of shows you, when we're doing complex mathematics, when to use sort of the real and imaginary part and when to use magnitude and phase. When it comes to addition, the real part of the sum of two complex numbers is the sum of each real part. The imaginary part of the sum of two complex numbers is the sum of the imaginary component of each part. But the magnitude of the sum of two complex numbers is not the sum of the magnitude of each part, or the product, or any other thing. We can't determine the magnitude of the sum of two complex numbers with knowledge only of its magnitude. We have to know both the magnitude and phase to determine that. Same thing with the phase. I can't determine the phase now of the total voltage here by knowledge of the phase of the plus wave voltage and minus wave voltage. The phase is whatever the phase is. We simply have to write down the complex expression and then determine that phase. It, generally speaking, is not pretty. We don't get the proportional to z behavior that we see for each wave individually. And you can kind of see what happens. You have two different waves, two different magnitudes, two different relative phases. They propagate in opposite directions. They add together at every point. At some places, again, they add together in phase and get larger, other phase and get smaller. The actual values at each location is simply whatever the math says it is, but we can't determine it simply from the analysis of each individual wave. If we had a situation where the telegrapher equation said it was a product of two propagating waves, things would be easier because, of course, the magnitude of the product of two complex numbers is the product of the magnitude, and the phase of the product of two complex numbers is simply the sum of the phase of each. But alas, the transmission line, the telegrapher equations rather didn't give us a total voltage in terms of the product of two terms. It gave us in terms of the sum of two terms, and where we're interested really in the magnitude and phase of those values, describing the magnitude and phase of the oscillations, this addition can cause us mathematical problems. So just be careful. Think about before you write things down. So I have asserted that there are two propagating electromagnetic waves propagating along a transmission line, one in one direction and one in the other, and each manifests itself in terms of a voltage and current. And so I talk about a function V plus as the plus wave voltage and V minus as the minus wave voltage. And so I throw a lot of words with wave in there around, and we look at the math and the complex functions, and we're not quite sure why we call them waves. We can determine the magnitude and relative phase of the sinusoidal oscillation at each location on the transmission line from their results, but there's nothing really inherently in those results that would tell us that there's a wave propagating along our transmission line. So to see physically or to see mathematically, rather, the physical manifestation of our propagating wave, we need to go through and write our plus wave and minus wave voltages in terms of their real value. We're going to go through and convert our otherwise complex expressions for the plus wave voltage into a real valued voltage. And of course we do that by multiplying the complex function by e to the j omega t and then taking the real part. And we do that, we pull out the real valued voltage and see explicitly the sinusoidal oscillation at frequency omega. And so this is the real valued representation of our plus wave voltage. Notice that it is a function of both position and time, and we can see that explicitly in the argument of the cosine. We have omega t for one term, and we have minus beta z for another term. These two terms together are the important terms. We find that in the argument we have omega times t. Remember, omega is the temporal frequency in radians per second. And then we have another term, we have beta z, where beta is the spatial frequency in radians per meter. And we see this subtraction, a minus sign here. And so the argument is based on the difference of those two things. And so this is kind of the hallmark of a wave propagation, is of course it has to be a function of both space and time. And we often frequently see that they manifest themselves in terms of a time and spatial term, and often with the minus sign there, they're kind of playing against each other. So let's see if we can see, I contend that from this we can see there is a propagating wave, but let's look a little closer to make that clear. First thing we're going to do is we're going to hit the pause button on our electromagnetic wave. We're going to evaluate this plus wave voltage at one specific time, and that time is t is equal to 0. All right, so again, you kind of think of this as hitting the pause button. And when we do that, t is equal to 0 and evaluate it, we get this result here. Notice in our cosine, we don't have a constant. We have a argument that is varies with position z. Doesn't vary with time anymore because time is fixed at 0, but it changes as with respect to position z. So what we have now is basically a sinusoidal function with respect to position z. And this says that the voltage, the plus wave voltage, will have some values, generally non-zero value, at each and every point z on our transmission line. How does that value change along the transmission line with respect to index position z? Well, it changes as a sinusoid, not time varying, but spatially varying. So let's look at that next. Spend some time then looking at this plot. So we're plotting now the plus wave voltage as a function of position z now. This is not as a function of t, it's a function of z. And so we plot it because the cosine, we see a cosine function that goes along there. Remember, the index z corresponds to locations on the transmission line. And to try to emphasize that, I put the transmission line just below this plot to see that z is equal to 0 is 1 in the line. Z is equal to minus L, in this case minus 2.5 is on the other end of the line. As we move up and down the transmission line, we find that the voltage will increase and decrease in a sinusoidal fashion. Now again, this is for one time 0. We've paused it, and so we've gone through and we've plotted instantaneously what the voltage would be at every location on our transmission line. And we see that it is sinusoidal in nature. If we were to look conversely at one point on the transmission line while allowing the time to be a variable, we would see that likewise we get a sinusoidal variation there. We get a magnitude oscillation up and down. at that point. But again, we're not allowing time to change. We're going through and hitting the pause button and stopping it. And if we go through and look at the voltage at every point on our transmission line from one end to the other at this single time t, this is the function that is traced out, a sinusoid in space, in addition to one in time. All right, now we're going to go through and hit the play button again, just for a moment, and then hit the pause button once more. We're going to do the same thing as before, but instead of plotting the voltage as a function of position on the transmission line at time t is equal to 0, we're going to move further in time to a point in time, such that t is equal to pi over 2 times omega. And if we do that, we get this result. And now this looks very much like what we got earlier, where we had time t is equal to 0, but it turns out it's not quite the same function. It's still sinusoid as it was before, but it has shifted to the right, or it appears to have shifted to the right. So let's look at that closer. So we plot the function now at time t is equal to 0. So this is at t is equal to 0. This is the voltage as a function of position along our transmission line at time t is equal to 0. And now this is our new function. Again, the voltage is a function of position along our transmission line z at a new time, frozen time, pi over 2 omega. If we look at these, we see they don't align up. There's one's been shifted in front of the other. And again, I've contended that essentially the second plot is the first one, only shifted to the right. This peak here is shifted here. Of course, that's a little bit ambiguous to say. We could say that, this peak here shifted to the left to here, and that's what we're actually seeing. With all the periodicity, there are many different solutions that would allow the original function to shift to this one here. But again, I contend it's shifting to the right. And to show that, what we've done sort of mathematically here is tag a point on a function at z is equal to, let me be 0.75. We've put a value there, and it happens to be 0. And then if we were to watch as a function of time, from t is equal to 0 to t is equal to pi over 2 omega, instead of jumping from one to the other, we sort of watched it continuously. What we would see is that blue dot would slide to the right. The entire plot would slide to the right. And then when we stopped it at the second time, we would get this function here. And notice the blue dot now is right here. So it slid to the right as we moved from time t is equal to 0 to time t is pi over 2 omega. And that's what we have. We have a wave that's propagating down the line in the direction of increasing z. These wave crests propagate, move, slide along as a function of time down the transmission line. Here again, I want to show, we talked about this earlier, the voltage, the plus wave voltage exists everywhere on the transmission line for all positions and all time. It doesn't exist simply at one end of the line, or the other end of the line doesn't exist on the top conductor or the bottom conductor. It's voltage between the two conductors, and we get a non-zero voltage, generally speaking, at every location along the transmission line. So we can do a similar procedure with our minus wave voltage. We can extract the real valued voltage for the minus wave voltage as a function of position and time. Again, multiply by either j omega t and take the real part, and we get this sinusoidal function, again with one term with omega t and the other with beta z. In this case, the only difference really is the sign here. We get plus beta z. And how does that change our results? If we were to plot this minus wave voltage at time t is equal to 0, we get something that looks essentially the same as what we had before. If we go through and plot that same function that's a short time later, once again we see that's a sinusoid function as a function of position z, again, that we're plotting here. But in this case, we see that again, the two functions are no longer aligned. One has slid in relation to the other. If we attach our little dots to try to figure out which way it's sliding, we find in this case it's sliding to the left. As time goes on, the crests of this function will slide to the left, and this indicates then an electromagnetic wave propagating in the direction of decreasing z, in the direction where z is becoming more negative, in this case, of course, then from right to left. One of the interesting questions about all this is, what is the velocity of propagation? And we can go through and do a little calculus, take a derivative, and try to figure out from this the derivative of position, derivative of z with respect to t. And when we do that, we end up with a result which is very simple. It is the ratio of omega to the value beta. The ratio of omega to beta is the velocity at which the wave is propagating, the electromagnetic wave is propagating. And if we had in free space, we would find that that value is exactly equal to c, the speed of light. Once we have dielectric in our transmission line, it'll slow that propagation down by inverse of the square root of the dielectric. But there's no surprise that it should be the speed of light, because it is propagating waves. There are propagating waves that manifest each of these two plus and minus wave voltages. So if we look closer at the math, we can see that there is a propagating wave. We've shown it here by plotting, tried to show it at different times. You can see that the two waves are sliding in opposite directions with respect to each other. And again, this happens at the same time. It's not they don't try to avoid each other or take turns. Since electromagnetic waves have no mass, they can pass through each other without any affecting each other.